All right, in this video we're going to talk about Unit 6, Objective 3, differentiation. So a function f of x is differentiable if the derivative exists at the point in question. Now, algebraically, this is not going to be anything new. Take a derivative, plug a point in, does it exist or not? But graphically, this is where things get a little bit different. So graphically, the derivative is not going to exist if the graph has one of these following things. Any point of discontinuity. So if you are looking at like a hole in the graph, not differentiable. If you're looking at a jump, not differentiable. If you're looking at an asymptote, not differentiable. So anytime you have to pick up your pen to draw the graph, not going to be differentiable. A corner, actually let's go down here to cusp. That's going to follow your way. A cusp kind of looks like a wave. So it looks like it's curving on both sides of the little point we have there. It could also be a curve and then a straight line, would be a cusp as well. A corner is just going to be two straight line pieces. So we're not going to be differentiable at any of these little points here or here. Now note on the AP exam, you can call corners cusps and you're going to be fine. So everything here you can call a cusp. And then oscillation is one that you're not really going to see, but what it would look like is if you have a function that's kind of going like this back and forth, and then it does it real quick in the middle, and then it kind of slows down again. This is alternating back and forth so quickly that we have no idea what's going on there, so the derivative won't exist. This one, oscillation, is not going to show up on your AP exam, just the first three. So let's look at an example, kind of see what's going on with these things. Show that the function f of x is x squared plus 2 if x is less than 1, x plus 2 if x is greater than or equal to 1, is both continuous and differentiable at the point x equals 1. So we know continuous, what that means. So we have to show that the limit as x approaches 1 of f of x is equal to f of 1. That's what we have to show for continuous. So for the limit as x approaches 1 of f of x, well, the function's two different things on either side, so we have to show both pieces. So we have to show the limit as x approaches 1 from the left of f of x, and that's going to be 1 squared plus 2 is going to be 3. We have to show the limit as x approaches 1 from the right of f of x, which is going to be 1 plus 2, which is 3. So these things match, so our limit is 3. F of 1, we're going to use the bottom piece because that's the or equal to, so that's 1 plus 2 equals 3. So we're going to say it's going to be continuous because the limit as x approaches 1 of f of x equals f of 1, which is both of those things equal 3. So this would be our justification on an AP exam for continuous. So we've shown that part, and differentiable. So this is going to be a little bit different. If you think about what derivatives are, they're the slope. But when you think about the actual limit definition, it's really a limit. It's the limit of the slope. So we have to make sure that the limit of the slope on each side equals the same. So really what we need to look at is the derivative. The derivative on the left, or the left-hand derivative, is what it's called oftentimes. So the left-hand derivative. So the derivative of the left side is 2x. So f prime of 1 is 2. The derivative on the right-hand side is going to be 1. So f prime of 1 equals 1. And I have a typo. I copied down the wrong question here. So this should say continuous and not differentiable. And we know it's not going to be differentiable because we have two different derivatives. So the derivatives would have to be the same. If we took the derivative here and we got 1, then the derivative on the left and the derivative on the right would be 1. So looking at this one, we can kind of look at it and see, all right, which of these types of non-differentiabilities do we have? Well, if we have a derivative of 2 and then a derivative of 1, we're going to have either a corner or a cusp. And looking at what this is going to be a curve. So it's really going to end up being a cusp. And that's because we have two derivatives that are not the same thing. So it's continuous, but it's not differentiable. So let's look at the next example. Same thing, show it's continuous, but this time I actually wrote it correctly, not differentiable at x equals 0. So continuous, we're going to have to say the limit as x approaches 0 of f of x. Again, it is going to be, actually we don't have to worry about the piecewise part because x times 1 over x is both sides of 0. So if we think about that, we plug in 0. As we get really, really close to 0, 1 over a really, really, really small number is going to give us infinity. So we're looking at 0 times the sine of infinity, which looks like it might be indeterminate, but remember, sine is just going to bounce between -1 and 1. So our limit is going to be 0. We know that f of 0 is 0 based on this, right? When x is 0, the function is 0. So we're going to say continuous, and then we're going to say because the limit as x approaches 0 of f of x equals f of 0 equals 0. So the limit equals the y value. Now looking at the differentiable part, the left-hand derivative is going to be, we have product rule here, so it's going to be sine of 1 over x plus, so this is x to the negative first power, right? So we're going to say negative x to the negative second times cosine of 1 over x times x. So there's our derivative on the left. The derivative on the right is just 0. So as we're looking at this, as this goes to infinity, or I'm sorry, as this goes to 0, we have like sine of infinity again. And then we have minus, if we have x over x squared, we really just have 1 over x, and then cosine of infinity. This is going to make this whole thing undefined right here, though, right? When we plug in 0. So if we have an undefined slope, that means we're either going to positive or negative infinity. We're subtracting, so really we're going to be going down to negative infinity, which means we have an asymptote. So our graph would look like this. We're going down to negative infinity, and then a slope of 0 at the middle, and then negative infinity again. So this is not going to be differentiable because this does not exist. This does not exist because we have 1 over 0, which is undefined. An undefined slope goes to infinity or negative infinity. This part really isn't important, but what this shows us is that we have an asymptote, which is going to mean we have a discontinuity. If we were asked to find the type of non-differentiability. And AP is not going to ask you to find that. They're just going to say, is it differentiable, yes or no? And since this derivative doesn't exist, it can't equal that derivative, so we're finished. So, last thing that I want to mention is that differentiability is going to imply continuity, but continuity is not going to imply differentiability. What that means is, if AP says something is differentiable, they do not have to tell you that it's continuous. You automatically know. But if they say continuous, that does not necessarily mean you're differentiable. So differentiability implies continuity, but continuity does not imply differentiability. So that's going to do it for this video. We will see you in the next one.